Okay, so probabilistic knowledge representation. So what do we want in a knowledge representation? We need to write down what's true, and we need to be able to do inference. And with Bayes nets, we're going to talk both about approximate inference and exact inference. Just like with first-order logic, inference in Bayes nets is pretty computationally challenging. I think it's actually more like propositional reasoning. It's sort of NP hard, I think. I'm not sure there's anything in Bayes nets that's piece-based. But anyway, exact inference is tough. So there are lots of approximate methods that people use. So we'll talk about approximate inference, where like you get the right answer. It's like close to the right answer. Usually you're trying to compute some probability. And so instead of getting the exact probability, you'll get a probability that's close to the true one. So we'll talk about both how to represent uncertain knowledge and how to do inference with it. OK, that's a Bayes net. Circles and lines. Now, we see circles and lines a lot in this class. So don't get confused with some of the other circles and lines you may or may not have seen before. These are not states in a state space search that get expanded. These are not states in an MDP that you might transition between. These are the propositional variables. This represents, there is a burglary at my house. This represents, there was an earthquake at my house. This represents, my alarm is going off at my house. This example is due to Yuta Pearl, who is a professor at UCLA, so he lives in Los Angeles. So burglary and earthquakes are like everyday occurrences. Here's the alarm going off. Here is his neighbor on one side calling him, saying, Yuta, your alarm's going off. And this is a proposition that Mary, his other neighbor, calls him and says, Yuta, your alarm's going off. So these are the variables. And so in normal propositional logic, you'd say something like, earthquake implies alarm. Like, if there is an earthquake, the alarm will go off. And if an alarm implies Mary will call, or something like that. Like, everything's very binary. Like, if this is true, then that is true. But here, with a Bayes net, we can start to get a little probabilistic about it. We can say, if there is an earthquake, then my alarm will go off with a certain probability. If you have a house alarm, they can be sensitive to shaking. I actually lived in Los Angeles for a year, and my girlfriend was living in San Francisco, and there was a huge earthquake, but I was in San Francisco at the time. So I came back, and all my spices had fallen off my spice rack, and there was a big crack in the driveway, and that was it. Like I got the aftershocks, which were really fun, but I missed the big quake. I was really disappointed to have lived there for that long and not miss the earthquake. Some people were killed, but not where I was living. So I felt bad about that. But anyway, so there are these variables, and they represent propositional, like something that could be true or false in the world, like my alarm is going off. But we have only probabilistic knowledge about these things. Now, the variables are related to each other, and that's where the arrows come in. Are we good, Frank?
I'm great.
Yeah, you look happy. Variables are related to each other. That's what the arrows are all about. These say that if you're trying to figure out whether alarm is true, it's relevant to look at burglary and earthquake, because those are things that directly affect whether the alarm is going off. Okay? And that's what these lines mean. Now, it's not just all circles and arrows. There are numbers too. So these are called conditional probability tables, and there's one of them for every variable. If you have no parents, if you're a variable that has no in-arcs, there are actually no conditions. So it's just a blatant probability. It's the prior probability that burglary is true. So the prior probability that burglary is true is 0.001. So 0.1%. The prior probability of earthquake is larger, is twice as large, is 0.002. And now this conditional probability table, or CPT, this CPT tells us the probability that alarm is true given the values for the parents. So if there was a burglary and an earthquake, the chance the alarm is going off is 0.95. Not 100%. It's not the world's greatest alarm, but it's got a pretty high chance of going off. If there's a burglary, almost as high, 0.94. I mean, the earthquake bumps it up just a teeny bit. If there was an earthquake, the chance it goes off it's less than 0.5, but it's still significant, 0.29. If neither burglary is happening nor an earthquake, then the chance the alarm's going off is 0.001. So small chance of false alarms. So does everyone understand the structure of these things here? And then you've got probabilities for these given alarm. And now there are interesting phenomena that happen in a Bayes network where if John calls, immediately, even before you pick up the phone, the instant you see the caller ID, you could imagine starting to wonder, gee, my neighbor's calling, is there a burglary? I better answer that. I'll take this one. You can say, well, okay, the prior of a burglary is 0.01, but if the alarm is going off, John's going to call with probability 0.9, which is pretty high. So the fact that and there's only a small chance he would call if the alarm's not going off. So just having him call provides evidence for the alarm, which provides some evidence for burglary. So we have indirect flow of evidence here from John calling back to the parents of alarm. So these are the kinds of things that a Bayesnet will let you actually compute with exactitude. We can compute, if we wanted to, the exact probability of burglary given that we know that John has called. Dylan, did you have your hand up?
Yeah. So what if you had both indirect and direct flow from one state to another?
So we can do it all. The reason we cover Bayesnets, even though they're only 30 years old, this is stuff that was developed in the mid to late 80s. So it's fairly new in AI, like compared to state space search, which was around in the late 60s and early 70s. It's pretty new, but it's very general and powerful and comes up all over the place, and it really works. In fact, we're going to be able to answer queries of this general form. So I have the values for some variables in the network. Give me the probability distribution over all other variables. Or give me the probability distribution over some variable I care about, x, given that I have some evidence for e, and then there are other variables, y, that I have no information about whatsoever. Like maybe I know there was an earthquake, and I know that John's calling, but tell me what the probability of burglary is. And there are other variables like y, like Mary calling, that I really could not care less about. So we're going to be able to answer like general purpose queries of this very flexible form. Tell me the probability that x is true and the probability that x is false. That's the distribution over some Boolean variable x, given some evidence variables and some other unobserved variables. So we're going to be able to do all that. Very, very wonderful formalism. Dan?
So am I thinking about the probabilities correctly?
Yeah.
If I take from this that if an alarm goes off, there is less than half the time it is going to be because of a burglar?
Oh, wow. That requires computation.
Okay.
Oh, man. You want me to actually compute something. The alarm is going off. What's the probability there's a burglary? Wow. You want me to do real work.
But just looking at it, it looks like the alarm goes off 0.001 when there's a double false.
Yep.
And a burglary happens 0.001.
Yeah, see, that's the thing, is you need to take these priors into account. Using Bayes' law, Bayes network, woo! The Bayes thing comes home to roost.
Every time that a burglary happens, then that's going to be less.
This has, so there's twice the prior on earthquake, but you're saying earthquake is less than half as likely. So if the alarm goes off, chances are it's a burglary. I think you're probably right.
Yeah.
Is that the kind of thing that I would accept on an exam? No. Like, we're going to need to do the computation, but I haven't told you how to do it yet. Yeah. Was there some other comment? Okay. We got our BayesNet, we got our CPTs. Fantastic. So people call this, in addition to calling it a BayesNet is a special form of what's called a graphical model. So you may hear people talk about graphical models sometimes. And what they mean is not that it's a pretty picture you can draw, but that it's a graph with vertices and edges. There's a special, well, I don't know that much about them, but if you don't draw arrowheads here, that instead of, if they're just undirected edges, that instead of being a BayesNet, it's a Markov random field, which sounds really fancy. But I don't know that much about them. I barely know enough about BayesNets to lecture about them, so I'm going to keep to BayesNets. Okay. BayesNets. You've seen graphical models before. We just didn't write them down as such. So, for example, k-means is, there was that what cluster are you, and then that determined your data values. So we had as a BayesNet, it would look like this. Here's a discrete variable that can take values, an integer value saying what cluster you belong to. And then there's a conditional probability table here that says, well, if you belong to one cluster, then you're distributed according to this Gaussian. If you belong to a different cluster, you're distributed according to some other Gaussian. And these variables were real-valued vectors. Like, I think in class, I guess we had a 2D Gaussian, so it was x1, x2 maybe, or xy, or two real variables. So this is the graphical model for a mixture of Gaussians that we fitted with k-means to some data last time. A naive Bayes classifier is just like every feature is completely independent. And they're totally not related to anything. So that's a naive Bayes graphical model. We did MDPs. MDPs, I guess you could say, there was S, and MDPs we have to use a slightly different notation that I really don't want to go into, but we had S, and you got to choose an action A, and the next state, the distribution of the next state variable depended on the state you were in and the action you took. A isn't really a random variable because you get to choose it, so that's why it's a box rather than a circle. Anyway, so you've seen some probabilistic models so far, but we just haven't written them down in this BayesNet-y kind of picture.